Hello students. In this video, let us discuss about electromagnetic induction, that is Faraday's laws. Okay? Faraday's laws. Right? For this, let us take a coil. Okay? Coil of wire. Connect both terminals of this coil to a galvanometer. Okay? So, firstly, there is no current or potential difference across this coil of wire. So, potential difference is equal to 0 in the coil. Right? Now, take a bar magnet. Okay? Now, bring this bar magnet towards the coil. Okay? You just bring the bar magnet towards the coil. Now, these are the flux lines of a bar magnet. So, already in last videos, we discussed that magnetic field is nothing but composed of magnetic flux lines. Okay. So, flux lines means the imaginary lines drawn along the path of a unit north pole. Okay. In magnetic field. Now, magnetic field will be in form of flux lines. Now, when bar magnet is coming towards the coil, we find deflection in galvanometer. So, what is galvanometer? That device or instrument which detects the presence of current. If current is there only, it deflects. If not, it doesn't deflect. Now, this is case 1. In case 2, you take a bar magnet away from the coil. Case 2, away from the coil. When you take the bar magnet away from the coil also, you will find the same deflection in the galvanometer, but in a reverse direction. First, if deflection is towards this, then deflection will be towards this, but in reverse direction. Which shows that this reverse direction shows that current changes its direction depending on motion of magnet. Okay. So initially there is no potential difference in the coil, no current in the coil. But when bar magnet is brought nearer to the coil, it galvanometer suddenly deflects. At the same time, when bar magnet is moved away from the coil also, we see the deflection in the galvanometer but in the reverse direction. Okay, so here the current direction is changing. It totally depends upon the motion of the magnet. And here another thing we can say that here we are moving the bar magnet. Now in case 3, bar magnet will be at rest position and coil moves. You move the coil towards the magnet or move the coil away from the bar magnet, you will find the deflections. Right? Now, in fourth case, in case 4, both coil as well as bar magnet are in motion. At that time also you find the deflection in the galvanometer. And in the last case, both are at rest. When both are at rest, we will not find any deflection in the galvanometer, which clearly says that if magnet is in motion only, or either magnet or coil, or either both must be in the motion. Then only we find the current in the coil. If not, current will be zero. If either coil and bar magnet both are at rest, the current will be zero. Okay. So now, depending upon these experiment, let us discuss about Faraday's laws. Okay. So now here, what we are saying, when bar magnet is brought closer to the coil, the galvanometer deflects. Means it is clearly proving that the change in a magnetic field give rise to the induced EMF, electromotive force. Induced EMF itself means a current is associated with it. So we are talking about induced EMF means nothing but induced current is established in the coil. Right? EMF means nothing but the potential difference between the difference in potential between the ends of this coil. Okay. So now this experiment clearly proved that the motion in a magnet towards the coil or motion of coil towards the magnet establishes the induced current. So now here, what is happening? As magnet is approaching towards the coil, means the magnetic flux lines are linking with the coil, no? Okay. When magnet is moving towards the coil means the flux linkage with the coil increases. Can we say? Yes, we can say. The flux linkage with the coil increases. And this flux linkage with the coil establishes an induced EMF in the coil. So, induced EMF means nothing but an induced current is associated with it. So, now we can say that similarly, when this is in the case when bar magnet is moving towards the coil. Similarly, when bar magnet is moving away from coil. Okay. So when it is moving away from the coil, what happens? The flux linkage with coil decreases. Okay. Again, it establishes induced EMF, thereby the induced currents. Okay. So either the flux linkage increases or flux linkage decreases means nothing but the change in magnetic field. Right? Here uniform magnetic field is not there. It is increasing. Here in second case it is decreasing, means here change in magnetic field is happening. So we can say that the changes in magnetic field establishes the induced currents in the coil. As per Orsted's theory, what he said, the change or stationary, here either stationary or the change in charges establishes magnetic field around the coil in current carrying wires. Okay. So magnetic field establishes in current carrying wires. Means electric field changes into magnetic field. Here compulsory the magnetic field has to change, because in last experiment when both are at rest we are not finding any deflection in the galvanometer, which clearly indicates that there must be change in magnetic field. So changes in magnetic field establishes electric fields, and this theory we call it as electromagnetic induction. So now let us state the two Faraday's laws. The Faraday first law. Faraday's first law. Okay. The first law says that whenever there is change in magnetic flux linked with coil and induced EMF is set up or established in a coil. This is the Faraday's first law. I think you are clear. Faraday's first law. Okay. Now next, what he is saying we are writing in mathematical form. What he said, induced EMF. How this induced EMF he is getting? When the flux is changing with respect to the time. When there is a change in flux with respect to the time, we are getting induced EMF, or induced EMF is established in the coil. Alright. So now EMF we denote with epsilon. Change in flux, flux is denoted by pi, time dt. Change in flux d pi by dt. Minus we will write. So the induced EMF established, how could I write the statement? The induced EMF established or set up in a coil is equal to negative rate of change of magnetic flux linked with a circuit or linked with a coil. This is the Faraday's second law. Now next, the major question is why we are saying negative rate of change of magnetic flux. Negative minus d pi by dt we wrote. Now this about the negative as well as what will be the direction of current. If we know the direction of current, then automatically we will understand why we kept minus sign in this equation. For this, stay with my channel Reshma Physics to know about this negative sign and the direction of induced EMF in my next video, lens law. Thank you.